Yes, good morning, everyone. Welcome to this lesson. Uh, I'll start by asking for forgiveness because I was waiting for you in the online class, only to discover I had not sent the link. I put it in WhatsApp, but I didn't press send. So it's after 12 minutes that I discovered something is wrong. And so I may not be very clear our call today. So, but I hope uh, you'll be able to get my voice. We will continue to look at what we were looking at the last time. We were looking at the concept of entropy, which is actually the average information, uh, average rate of information. And you can see that's why we are working with all the bits, because whenever you talk of uh, entropy, you are talking about uh, average. We call it average because we are talking about per symbol. You are considering all the symbol and considering what is the average per symbol. So it is always in bits per symbol. It's not averaged over time, it's not averaged over the symbols. So that is the average amount of information associated with the source and this bits per symbol. Uh, and we also learned that the entropy, the maximum entropy is just the log 2, the number of symbols. That is the maximum. So in the case where you have two symbols, uh, for example, the binary case where we have 1 and 0, then the maximum entropy is 1. Uh, it just depends on the size of the alphabet. So when you have more alphabets, the average entropy is greater. And it makes, intuitively, it makes a lot of sense because as we are going to see, as we are going to see uh, later in this lesson, is that the average, the entropy is actually the amount of uncertainty. Yeah, is the amount of uncertainty, uh, and it still depends on what entropy you're talking about. So if you talk of the entropy, input entropy, which is the hx, then we are really talking about the uncertainty uh, of really knowing which symbol it is before before you have seen the output. Because when you have seen the output, of course, that becomes now conditional entropy. Yeah, but when you talk about the marginal entropy, because hx, I think you remember those terminologies where especially where you have uh, uh, where you have two different events, then you can have the marginal entropy of each. of those. You can have the conditional entropy, uh, one given the other one, or you can also have the what you call uh, the joint entropy, considering the entire the two different uh, events. Yeah. So what you're going to look at today is I think we did look at this. We looked at the memory resource, and we looked at the different type of channels. So by now, I think we know that a channel, a DMS, a DMC, that is a discrete memories channel, can be fully specified or described by its channel matrix, which is a matrix of transitional probabilities. And we are talking of two probabilities because we have the input and the output. So we have the probabilities that that the symbols at the input will be this, and we have the probabilities of the output symbols will be this, which is now the PY. And we are saying that the two are connected, or the two are related by the matrix of transitional probabilities that we call channel matrix. And we are going to see that this is very critical if you come to getting the information rate, yeah, of a channel. So we looked at the different types of channels. We saw there is a lossless channel, and we said this channel is described by a certain type of matrix, channel matrix. But we just said lossless means there are no losses at all. You can also have by no losses. What we mean is that when you are sure you are the probability, we are sure of the output. Otherwise, uh, you can have a channel which is not noiseless, but yes, it's lossless. Yeah, but a noiseless channel, of course, will be both lossless and deterministic. So once a channel is noiseless, of course, it will also be lossless and it will be deterministic. But a channel may be lossless, but it's not necessarily noiseless. But once it's noiseless, it's both lossless and deterministic. I think we looked at all the scenarios, what makes the lossless channel and what makes the noiseless channel. And actually, I think we can get back to where we were when we were looking at that. I think that was a lossless channel. Yeah. So those are the channels. The lossless channel, when you have an input symbol X, the output is not necessarily, when you have X1, it's not necessarily Y1. There will be a probability that it is Y1, and there will be a probability that it is Y2. Yeah. And this is what we call a lossless channel. So we know once we get Y, for sure the input was X1. And once we get Y2, we know the input was X1. Yeah. So we call it a lossless channel, although the probability is not 100%. But when you have X1, you're going to get Y1. There's a 3/4 possibility that you're going to get There's a 0.75 probability that you're going to get y1 and 0.25 probability that you get y2. But the moment you get y1, you are sure that what was sent was x1. The moment you get y2, you're sure that what was sent was x1. Yeah, that's why we call it the lossless channel. Yeah, deterministic is this one. A channel. This is a matrix of deterministic, and we are saying that if you have x1, you are sure that you are going to get output y1. That's why we call it deterministic. And if you have x2, you are sure you're going to get y1. Yeah, but y1 you can get either x1 or x2. So that is what we call deterministic. Yeah, and this matrix would be something like this. Yeah, and of course the last one is the noiseless. Noiseless. Once you have y1, you are sure the output will. Once you have x1, you are sure the output will be y1. Yeah, and once you have x2, the output will be y2. And this is what we call a noiseless channel. So it is both noiseless. I mean, it's both deterministic and it's both deterministic and also lossless. Yeah. So I hope you're able to appreciate the differences. Yeah. The other channel we are going to look at is the binary symmetric channel. And with this one, the transitional, the matrix of transitional probabilities, which we call the channel matrix, is given by this, where P is the probability that when you send a 1, you get a 0, and when you send a 0, you get a 1. Yeah, so that will be a binary symmetric channel. And if we have any calculations, very likely we will stick to this binary symmetric channel because it's a simple channel. Yeah, and this one, why you call it binary symmetric channels is because this is a case whereby you are sending zeros or ones. Yeah, when you are sending symbols representing zeros and ones, because sometimes these may not be the symbols, as we are going to see later. Sometimes the symbols are from a keyboard and there can be more than one. Yeah, the alphabet is not necessarily having only 2 elements, like in the case of the binary symmetric channel. Of course, we have another type of channel. I think this is not the channel. We have a yeah, okay. This is a binary symmetric channel, but we're also going to see that we have another type of channel. We will look at it. It's called the binary eraser channel. I was hoping we have it not in my notes, and what did we have on we can also have this kind of channel. Yeah. So it's not in our notes, but I thought it's good you know about it. But we will concentrate on this one, so we will not have even any calculation on this one. It's not in our notes. So this is the binary eraser channel. So we are saying it's also a binary channel, but it's not a binary symmetric channel. It's a binary eraser channel. We are saying that once you send a 0, there is a 1 minus p probability that you are going to get a 0. Yeah, and there is but there's no possibility that you're going to get a 1, but there's a possibility that you will not know whether it is a 0 or a 1. That's what we call this. We call it like the error E. Yeah, so this will be an error. So once you set an x1, you're either going to have a possibility, I mean there's a possibility 1 minus p that you're going to get a 0, and there's a P. So the P is normally the smaller probability, the one we are hoping it will be the smaller probability. We are saying in the probability that you will not be able to get either a 1 or 0 at the output. We call this a binary Elisa channel, as opposed to the binary symmetric channel, where there's a probability that you are going to get a 0 when you send a 1, or a 1 when you have sent a 0 at the input. Yeah. So that is what, let's go back to where we were. So that is the binary symmetric channel, and that is a channel, and that is its channel matrix. Yeah. Sorry. And like all channel matrices, you know that the I think it's good to know this. This means P y1 given x1, and this will be P y2 given x1. This is P y1 given x2, and this is P y2 given x2. There should be no confusion. Sometimes I see confusion. But always remember that the columns are the y's, so this will be y1 and y2, and the rows are the x's. That's the standard way of representing matrices. So that should not be a problem. So you may be given the binary channel, and then you are given the inputs, and you are asked to calculate the probabilities of getting various outputs. And of course, the outputs in the case of the binary symmetric channel is either or 0 or 1. So you'll be asked to give the probability of getting a 0 or getting a 1. The probability of, yes, the probability of getting a 0 or a 1. Yeah. So I hope nobody has issues with that so far. So I want us to look at something, entropies, different entropies, because the different types of entropies, because they will become very important when it comes to working out information rate. Yeah. So we have the marginal entropy H of x, which we call the marginal input entropy. Because remember, you are talking about a channel, and what you are saying is when you send certain symbols are the input. So the y's are the output, and what you are talking is we are talking about output at the receiver. Yeah, because we are discussing the channel. So when we talk of these conditional entropies, it's good to understand it in that context. That you have probabilities, because even which symbol is sent is probabilistic by itself. Whether it will be a 0 or 1 is probabilistic. But we're also saying even the output is also probabilistic, because some things may change. May change because of the channel noise and all that. So the marginal input probability is already what we have discussed. Is we use normally m for the input and n for the output. So we are saying h of x, the marginal input entropy, is given by this summation. We have already seen that. We are saying h of y again will be given by this uh, equation. Yeah. So here we are using the output probabilities, and here we are using the input probabilities. Now we are saying that this it should be 1 to n and I is equal to not n m, I to m. So we are saying the marginal, the conditional entropy. There are two conditional entropies. That is the entropy of x given y and y given x. This one is a long derivation, so I think we just master this. It's given by this, and actually it can be shown. It's a long, very long derivation. So I decided we don't go through the derivation. But it's just good to remember that it is given by the joint probability multiplied by the log of the input given the output. Yeah, if you are talking of input given the output, and it's good to think of what that actually means, because remember the entropy is actually uncertainty. That is why what has a low probability of occurrence have a higher entropy. Yeah, because entropy average information. Yeah, the average amount of information which you are calling entropy is actually the average uncertainty. Yeah, that's why the one with the less probability has a higher entropy. So when we talk of this, we are saying this is a uncertainty at the input. Average uncertainty, again, we are talking about average uncertainty because we are talking of different symbols. Yeah, because we are going from I to M. Yeah, we are talking of many input symbols because we are considering I to M. So we are talking about the average uncertainty. Yeah, because all of them have uncertainty. Of course, whenever you talk about probability, then you are also talking about uncertainty. Yeah. So average uncertainty, this is the average uncertainty at the output. Each of the symbols has its own uncertainty, and we are saying the average uncertainty is that. Now, this conditional entropy h of x given y, it means that is the average uncertainty after you have received y. Yeah. So before this would actually be, it means the uncertainty now will be actually less because once you have received y, the uncertainty reduces. Yeah. So this hx given y. Once you receive the y, the uncertainty reduces. And we are going to see what actually that means in terms of the information which has been passed. Yeah, because the information which is passed is actually that difference between uncertainty before there's uncertainty at the input before any output is received, and uncertainty after it is received. Yeah, and I think we are going to see uh, that uh, as we go. That's what we call mutual information, the mutual between the input and the output. So mutual information becomes actually the information which is passed, yeah, to the input. I mean to the output. That is the information which has been passed in that channel. That reduction in uncertainty is actually what we call the mutual information, which we are going to look at just in a few minutes. Yeah. Then h y given x. This is again the uncertainty of receiving the average, because again we are talking about the different symbols, output symbols, but the average is h of y given x. It means the uncertainty when x is transmitted. Yeah, the other case we were saying the input is like the input entropy once it has been you have already received y, but here we are saying the entropy when you know that x was sent. Yeah, that's what this this means, y given x. Yeah, and you can see the difference is just uh, for y given x when you talk of y j uh, given xi, and before x given y we see xi given yj. Just from the definition itself, uh, you can see how you get this. Yeah. Then there is hxy, which is the joint entropy. Joint entropy just given by that. Uh, so again, you can see there's always this factor of the probability, the joint probability applied by now the logarithm of the joint probability. Yeah, and it makes sense because now the joint probability xy is just like you consider the x and y just to be like x. So if it's x, it's pxi log 2 px I1. And the same thing, if you have got x1, y1, is simply uh, xi, sorry, not x1, I1, xi, yj is simply replace the xi with xi, yj, and the same here. Yeah. So that is the joint entropy. And this is how they are related. Of course, the joint entropy, again, this can be shown through, it can be shown that the joint entropy is simply the conditional entropy added to either the conditional entropy, that is x given y, plus the output entropy, and it's also the same as the conditional entropy y given x plus h of x. Yeah, these are the same. So you can either get it by using the conditional entropy of x given y. Yeah, the average uncertainty of x once y the output is received plus the output entropy, or the conditional entropy of y knowing x was sent plus the input entropy. So we say x, h of x and h of y are the average uncertainty of the channel input and output respectively. The conditional entropy, I think, is defined here is the average uncertainty of the channel after the output has been observed. Yeah. And the conditional entropy is average uncertainty of the channel output given that X was transmitted. Yeah. And you can all see the difference. And this Hx, which is the joint entropy, is the average uncertainty of the channel. Yeah. And you can see we associate h of x with a source, but we associate h of x and y, which we are calling the joint entropy, with the channel. So we associate the marginal entropy, especially actually the input marginal entropy, with the source. Yeah. And we associate the joint entropy with the channel. This makes sense because it's the channel that connects the input and the output. Any condition, any questions about this? Yeah, I think we can proceed. So we have this very important thing, the mutual information, because really it is a mutual information that lets us be able to calculate the channel capacity. Yeah. So the mutual information I, X, and Y, that's what this is what we call mutual information, is given by H of X minus Hx of Y. We are saying, because this one is the what do you call it? The uncertainty resolved by observing the channel output. Yeah, because you are saying this is uncertainty before, and this is the uncertainty after you observe the channel. So the mutual information is the uncertainty resolved by observing the output. Once you have the output, some uncertainty is resolved, and that is what actually represents transfer information. So mutual, that's what we call mutual information, represents the transfer of information. And it makes sense. It makes a lot of sense if you look at it, even in real life. Uh, of course, when you don't know something, you cannot. Well, you can guess, and there is uncertainty that you get the correct story. But once you have experienced now the output, I don't know another good example. Well, if something is going to happen, if you ask what is going to happen, you can only guess with uncertainty. You don't know what is going to happen. But once it has happened, once you know what is the output, there may still be some uncertainty, but the knowledge you have gained is actually the difference between what you knew before and the uncertainty. Yeah. After that, after actually the thing has happened. Yeah. Because even in life, most things are still probabilistic anyway. So I think we can be able to relate uh, with real life and probably be able to understand the concept of mutual information. Yeah. So mutual information can either be the input entropy, the input marginal entropy, uh, minus, we can call it the input conditional entropy, because there is a condition that you know why, you know, you have observed why, or it can simply be the output entropy minus the conditional entropy that y given x. Yeah. So it can either be this or this. Yeah. Of course, it means this is equal to this. Yeah. And that is what we call the transfer of information. Mutual information is represents the information transfer, and that's why it helps us to be able to calculate the channel capacity. Yeah. So you can see channel capacity per symbol. So it depends on the number of symbols you have. Channel capacity per symbol of a discrete membrane channel is defined by the maximum of the mutual information. And we are going to look at a case of how to get the maximum. We will do an example tomorrow of uh, maximum. Now we show cases whereby when either the marginal input entropy, output entropy is maximum. We also look at a case where the, the, the mutual information is maximum, because that gives us the channel capacity. Because really, channel capacity is talking about the maximum. When you talk about channel capacity, we are talking about what is the maximum amount of information that can be carried, yeah, by that channel, given that the channel is probabilistic. Yeah. And we are saying it's a function of only the transition probabilities that define the channel. I think what we are trying to say is traditional probabilities determine things like h of y, yeah, and therefore determines h of y over x, and therefore this is just a function of transitional probabilities as define the channel. And the best example is to see it from here, yeah, because to get h of y, you need to uh, to get y, and to get y, to get the output probabilities, you use. We'll see an example how you calculate the output entropy. Yeah. So, well, how you calculate the output probabilities. If you know the input probabilities, using the channel matrix, you can calculate the output probabilities. So you can get the output entropy, which depends on the output probabilities, by getting the transition matrix, or rather the channel matrix, to the transition probabilities. And of course, this itself is just uh, it depends on the transitional probability. Yeah. So CS is a function of only transitional probability that is find the channel. Channel capacity per second, of course, it will be given by the symbols, because we are talking about this is bits per symbol, because it has the same units as entropy. Remember, we said entropy is always in bits per symbol. Yeah, it's in bits per symbol. So even channel capacity is in bits per symbol. So to get, the channel capacity per symbol, actually CS is the channel capacity per symbol. Otherwise, the channel capacity is simply the channel capacity per symbols multiplied by the symbol rate. Yeah. So you can be able to get channel capacity so long as we know the output probabilities and the input probabilities. Yeah. Because you'll be able to get mutual information. Yeah. And therefore, at the maximum of that mutual information becomes the channel capacity per symbol, and the channel capacity is simply the channel capacity per symbol times the symbol rate. So it will be easy to see once you begin dealing with, let's say, symbols from a DMS source, uh, uh, from a DMS, which is actually a digital memory source, and what do I want to say? Yeah, where you have got more symbol than one, So there is a case whereby you have got more than one symbols, like the characters of a keyboard would be more than one symbols, but you also have symbols that represent zero and ones. So you only have two symbols. Yeah, that's the binary case. Yeah, but you may have cases whereby you're dealing with the symbols, but they are not. It's not the binary case. You have a number of possibilities, and most of our calculations data will be based, uh, especially when we apply now when we apply this information and entropy for coding. That is entropy encoding or coding coding symbols depending on the information they carry. Yeah. So I think we can stop there. If there are any questions, if there are no questions, and please do what you normally do, just post your registration and the chat. So if there are any question you can ask, otherwise tomorrow we can continue tomorrow morning at 8 in our double lesson. Yes, Samuel.
Yes, when you introduced Cloud Shannon's mathematical theory to information,
Yes.
I did not quite understand what the engineers before Shannon were, the communication engineers, what kind of approach they were taking when they were building the systems. It did not quite come clear to me. I think you
Ah,
mentioned they were doing ad hoc.
actually, there was, in fact, that is the whole idea about this theory, mathematical theory of communication. Before then, there was no way you could be able to predict the capacity of a channel. It's Shannon who made it possible. So they were still designing uh, channels, of course. They would communicate, but it's only we are only saying that they were not able to predict. They could not. They could not. You made a channel and hope for the best. But now you are able to predict, even when you are creating the channel, how much uh, uh, you can create a probabilistic model that is able to tell you how much you are going to get from this channel. No, there was no way. I think that's actually the answer. He is it's a Shannon who made it possible that you can be able to predict, calculate because before you could probably average, you could simply do measurements and find out how much channel information you're able to get across, the bit rate, yeah. But to predict was impossible. Yeah. I hope I answered your question somewhere.
Yes, thank you.
Yes. That's why Claude Shannon was a very important man in communication. So then we will stop there and we continue tomorrow. Have a good day.